A black hole was photographed from Earth, even though not even light can escape one. How is this even possible? We're talking about an object so extreme that the universe itself seems to erase it, and yet, scientists didn't just prove black holes exist. They made one look back at us. What they captured wasn't the hole itself. It was something stranger, the shadow of the shadow, carved out by gravity, light, and a telescope the size of Earth. A black hole is a region of space where gravity is so strong that once you cross a boundary called the event horizon, escape becomes impossible. Not for a rocket, not for a photon, not for anything. That's why the phrase "seeing a black hole" sounds like a contradiction. But black holes are not cosmic vacuum cleaners swallowing everything around them. Most of them are only visible indirectly by the way they bend light and affect nearby gas, stars, and dust. In 2019, the Event Horizon Telescope produced the first image of the black hole in galaxy M87, and later the black hole at the center of our galaxy, Sagittarius A. What we see in those images is not the black hole as an object, but a bright ring of hot material around a dark center. That dark center is the black hole's shadow, so the real question is not, can you see a black hole? It's, how do you photograph something that destroys the very thing cameras need? The challenge is brutal. Black holes are tiny on the sky, even when they contain billions of suns. M87's black hole is enormous, but from Earth it still appears incredibly small. To resolve something that tiny, you need a telescope with absurdly fine detail. A normal telescope just blurs it into nothing. Then there's the environment. The black hole is surrounded by superheated gas moving at extreme speeds. That gas glows, flickers, and changes shape. The image is not a still object sitting there politely. It's a moving target in a storm of plasma. And the black hole itself warps the path of light. Some light gets bent into rings. Some gets swallowed. Some gets boosted toward us by motion. As one EHT scientist put it, the shadow of a black hole is the closest we can come to an image of the black hole itself. So the problem was not just finding a black hole. It was separating the black hole's actual signature from a chaotic, relativistic firestorm around it. Here's the trick. Scientists did not try to photograph the black hole directly. They photographed the glowing gas around it at radio wavelengths, then used the black hole's own gravity as part of the image. Think of it like trying to see a black marble on a bright table. If the marble gave off no light, you wouldn't look for the marble itself. You'd look for the shadow it casts. Now make the table into a ring of blazing plasma, and make the shadow appear because gravity bends light around the marble. That's the black hole image. The Event Horizon Telescope is not one telescope. It is a global network of radio observatories working together as one giant virtual dish, effectively as large as Earth. By linking telescopes across continents with a technique called very long baseline interferometry, the team matched signals with extreme precision. That gave them the resolving power needed to detect a region only tens of microarcseconds across that when. The data had to be stitched together. Each telescope recorded the same cosmic target at the same time, but the Earth's rotation, atmosphere, and timing differences all had to be corrected. Supercomputers turned that mountain of raw data into a reconstructed image. What emerged was a bright asymmetric ring. That ring is light from hot gas orbiting near the black hole, distorted by gravity and motion. The dark center is the shadow, not because the black hole is a hole in space like a literal tunnel, but because its gravity traps photons that would otherwise reach us. In other words, we see the black hole by seeing how it bends, consumes, and blocks the light around it. This was a scientific breakthrough for two huge reasons. First, it gave direct visual evidence of a black hole's shadow, which strongly supports Einstein's general relativity in one of the most extreme environments imaginable. Second, it opened a new way to study objects that were once thought impossible to image. That matters because black holes are not just theoretical monsters. They shape galaxies. They launch jets of matter. They regulate how stars form. They may even help us understand how space-time behaves when gravity becomes overwhelming. And here's a surprising fact. The first black hole image was not taken with light in the visible part of the spectrum at all. It was made using radio waves, because radio astronomy can pierce through dust and is ideal for combining signals from telescopes spread across the planet. So the image was never about making the invisible visible in the usual way. It was about learning what the invisible leaves behind. A black hole can't be photographed like a mountain or a planet. But if you know how to read gravity's handwriting, even the universe's darkest objects leave a signature. That's the real answer. We didn't see the black hole itself. We saw the evidence that something impossible was there. If that blew your mind, drop your best guess in the comments. Hit like and subscribe for more videos about how this is even possible.